out from a course having some magic number in the head. 6 milliliters tidal volume. Why so popular? So easy. It's a Sumeric numeration, 6, 12, and so on. So it's something in the centuries we have in the soul. And everybody uses 6 milliliters per kilo. And this has to do, why per kilo? Has to do something with the volumes. I want just to jump again with some of the last proposition of Brochard, because I think that the concept of the respiratory system is made by two elastic bodies which are connected at the same volume, which are the lungs and the chest wall, is not easy to digest, but is essential to understand or to try to understand what's going on in a given patient. And if you understand the mechanism, you can maybe try to fix the mechanism. And the survival with a side effect. Unfortunately, I arrived quite late. I saw the last slide of Mauri, and I start to laugh. What would you do? Whatever you do, in this case, without having some measure mode, you just have to take a coin and to lift up. If you would be your brother, you would like to know something more. So the relationship between the chest wall and the lung, which is the role of the pressure and the role of the volume, have to be fully understood. Not maybe for the majority of the patient, but of 3, 4, 6 patients that happens per year in a normal intensive care, maybe less than 5, which maybe didn't read the protocol, are out of the protocol, and you have to understand what's going on. And I think when we speak about tidal volume and this kind of thing, you are very young in this, but for at least 10 years, it has been a big debate in intensive care. Is a volotrauma or is a barotrauma? Which is the manifestation of the complete ignorance of the basic physiology. Because if you look at this part of the equation, transpulmonary pressure, you may call barotrauma. Barus is, I think, Old Greek, which is pressure. And if you look at this side of the equation, is tidal volume over the lung volume is the volotrauma. So I cannot play with this without touching this one. Because in between, we have one constant of proportionality. So when I increase the transpulmonary pressure, I say transpulmonary pressure, which is equal to the stress, I increase the deformation of the system, which is the strain. And how much are linked depends on the specific compliance, on the specific elastance. If you got this relationship, even numerically, I'm sure that you can see your patient with the different and innocent eyes. Physiology is great, but older you get, more you are back to the anatomy, because the anatomy is the basic of everything. And very simply, in the anatomy, there are people as Weber that probably 95% of you completely ignore Weber who. These are kind of giants who describe perfectly the structure-function relationship into the lung. And what basically Weber say, okay, we have a lung which is a network of fibers. And this network is done by elastins, spring, and inside we have a collagen, which is folded. The collagen can be unfolded but it's not extensible. Elastin is perfectly extensible. When I reach this point, everything is stopped. I reached my physical limit, which is the total lung capacity. And now you read, okay, if we use 6 milliliters per kilo even in normal men during anesthesia, you have very bad outcome. Wait a second. Tell me for what damn reason we are built to go from 0, let's say 200, and in a normal man we should have tremendous effect. We are going at 230. So don't believe too much of what you read and what you hear, including myself. But try to use your brain and to ask always why. Why this should be dangerous. Why everybody of us, every so often, take a big breath up to the total lung capacity. Of course, if I continue to try to put volume in this condition, when my system or safety system, which is collagen, is completely extended, I can break the collagen because all the molecules, bonds, are broken. At this point, I have a pneumothorax, blah, blah, and so on. A little before, we have what we call maybe excessive stress and strain without knowing exactly what we are speaking about. And let's see, experiments. The experiments usually are done to understand or to prove one theory or one hypothesis. With evidence-based medicine, we do the experiment to invent an hypothesis, which is a completely an upset of the normal logical reasoning. But what this tells you, that you take a normal, healthy, innocent pig, 25 kilos, that means lung volume is about 300 milliliters, and you ventilate with a strain of 1, 1.5, or 0.5, nothing happened. What is the strain of 1? Strain, you remember, tidal volume compared to the lung volume. So if my lung volume is 300, and I put a tidal volume of 300, the strain is equal to 1. It has to ventilate a man, normal man in anesthesia, let's see, with a tidal volume of 2 liters. It's absolutely crazy value. However, you take these pigs and after 3 days, with this kind of a strain, the lungs are perfectly healthy. You take out the lungs, are pinky, the gas exchange is okay, the compliance is perfect. However, when you reach a strain which is around 2.5 or greater than 2.5, for 24 hours nothing happened. After that, start something. I will show you some recent slide on that, where we start and how the things proceed. And in few hours, we have a lethal ventilation. You have a tremendous RDS, and the pig died. But my dear friends, this strain, 2.5, correspond to what? To the range of total lung capacity. If I have 1 liter of lung, my total lung capacity is around 2.5, 3 liters. If I had 300 milliliters, my total lung capacity starts around at 900 milliliters. And as not everything goes immediately, you have a range of total capacity areas. Some regions of the lung reach its own total capacity before or after, and other regions. But this gives you an idea. So the stress, this corresponds to a stress. And you see, these are pigs, and you see when the strain is between a right to 2, some pigs start to have problems. Some resist, but when it's greater than 2.5, no question. The death is for sure. And this is done in hundreds of animals, ventilated for 2, 3, 4 days. But look here, if you look at this graph, I will discuss this later, you see that at this value, at the strain of 1, the pressure, the transpulmonary pressure, is 5. If you do in men, it's far higher. And you see, you read a lot of literature saying protective lung ventilation in mice, protective lung ventilation in rabbits, in pigs, in dogs. I start to laugh because you apply to a mice number of concepts which are tailored with men, for men, which have a completely specific lung elastance. The constant of proportionality between pressure and volume is different in the different animals because the composition of elastin and the collagen is different. Very easy. Anyway, that strain is important. Look here, these are strain in the of 1, 2, 3, 4, 5, 6, and you see, this is the time to reach a tremendous situation of respiratory failure. And you see that you have, anyway, that greater is the strain, faster is the time in which you read. But back to men, women too. We have tidal volume per kilo. Why? Why we say tidal volume per kilo? It's quite obvious. Because one thing, a big man, big lung. Small man, small lung. So I normalize my tidal volume per kilo. As I don't have, but the tidal volume does not in the kilos, goes into the lung. So the concept is that the tidal volume, that kilograms of ideal body weight, which are tailored on the height, is a decent surrogate of the lung size. This is the only reason why I use milliliters per kilo. Is that true? Well, you see, my God, of course it's true. Look here, these are the body weight of the mouse, and here is the body weight of the elephants. And this is the logarithmic scale, of course. Logarithmic scale because you have to go from 0.1 grams to 1,000 kilos. And all the animals, the problem is that conceptually it's quite obvious. The lung of the elephant are a little bit bigger than the lung of the rat. But the problem is, how is within the different rats, there is a real correlation between the lung weight, the lung size, and the body, and the kilograms, and this in healthy. In RDS, we have some problem. Because what in RDS? The ventilable lung, which we call baby lung years ago, may be 200 milliliters, 300 milliliters, 400. The total lung volume is similar, but I change the gas with the edema. So the total volume more or less is the same. But the baby lung is completely different. So this was done at the good times in which it was enough to study 5 patients carefully to understand the mechanism. Now you have to study 3,000 patients to not understand anything at the end of the story, which is called evidence-based medicine. Anyway, look here. These are 200 patients, almost 200 patients, which were studied very carefully with CT scan 5 for 15. So whatever possible to measure in this patient has been measured. And you see These are the body weight, if I see correctly, yes. Let's see, 50 plus minus 3, ER 77 plus minus 3 standard deviation. In yellow is the tissue, which include the edema, and this is the lung, the amount of gas volume. And you see that there is, if your weight is 50 or the weight is 77, the dimension of the baby lung are not statistically different. Maybe you have a so huge variability. Does not depend. Here is the expected lung weight, which increase in blue a little bit with the body weight. But you know, thinking that tidal volume per kilo is a surrogate, even a decent surrogate of the lung size is simply wrong. Cannot be done. So, cancel in the mind, tidal volume per kilo. And the strain is tidal volume, not per kilo, but tidal volume per divided the lung volume. Here, ideal body weight, total gas volume measured with a CT scan. You know, in severe ARDS, you know, you have a lower gas volume in yellow, but you see it's perfect. It's still statistical. Okay, look, this is just a curious. You say P002, significant. But tell me, what kind of clinical meaning has a significant like that? When you may have, at 50, you may have 2,000 of gas volume. And here at 80, you may have, at 80, you may have 2,000 of gas volume. So for the individual patient, of course, forget the relationship between these two amounts. So, if you believe that the strain is important, you have to measure or to estimate it. And then I will discuss at the end the relationship between stress and the relationship with strain. So we have direct assessment. This is with a CT, with a helium, with N2, with so the gas dilution. And very briefly, the CT is, I think, is perfect in terms of measurements of the gas volume which is present into the lung. Why the helium and the washout of nitrogen have to do with the lung which is ventilated. In a CT, if you have a lung which is, or part of the lung which is hypoventilated, but is just kept full, is not measured by the dilution of the gases, is measured by the CT. Which doesn't mean that one is right and the other one is wrong. Just tell you that the information that you are given are different. And remember, sometimes the understanding in what you do not expect. So we'll see included ourselves the correlation between nitrogen, helium, and CT. But if I have a big discrepancy between helium and CT, this tells me a lot about the pathophysiology of that particular patient. Okay? So with the CT, well, you need, unfortunately, whatever you want to do with the CT, still now, when we speak about patient, we have to make a manual control. There has been, and there are, a lot of attempts to make this process more automatic or completely automatic. But as far as I know, at the moment, unsuccessful. When you have all the region of interest, which has been well defined, you can count how many voxels are there into and how much is the gas fraction in each of these voxels. You make the sum, and you measure the CT scan with the gas volume. Of course, you cannot take the patient back and forth with the CT scan because of several reasons. First, it's probably useless. Second, you have the radiation, and third, the logistics are really uncomfortable. If with all the spending review we have, you have 2 doctors and 20 patients, just forget about this kind of thing. You just simply cannot do it. Okay, but this is very good. This is an old T system. I think we are using this system since 1974-75, in which we had a tank with helium in oxygen and nitrogen, some concentration. We fill up a balloon with an amount known of gases. We disconnect the patient, you declamp, and this volume, and this is the volume we want to measure. Of course, we know the concentration at the beginning, then we start to put the gases in. When you have a good mixing of gases, the concentration here is equal to the concentration there. We disconnect, we go to measure the concentration, and you can easily, is a mathematics of that you study when you are 11 years old, so can be afforded, and you can compute the lung volume that we were measuring since 30 years with this system. Now, and well, this is 1979, and we were published in Italian, but you see, this is the amount of time of the total ventilation that you need to reach the equilibrium. If I take a balloon, I just make one, it's not enough. I have to ventilate the patient at least up to 6, 7, 10 liters. So if you have 1 liter and a half balloon, you have at least to make 15 in and out to be sure that you are reading the same concentration, so you have an equilibrium. And the relationship, this is the relationship between the helium and the CT scan. So I will not discuss the difference. Tell you just that there is a decent way to estimate the lung volume. The differences, when they are very large, may give you some information about that, because the helium depends on the ventilation and how a given region of the lung may be ventilated. Let's see, you have a patient with COPD, which may become more complicated. We have a patient in which you start with a very high PEEP, in which the ventilation is more complicated. So there are different conditions. One depends on the ventilation, the CT scan doesn't. Then now, I am not paid by the GE, but is one of the ventilator in which is the same concept basically. Instead to put helium, Elastin was using 25 years, SF6 was patented by Siemens but was never entered. Because, I mean, the technology to do this kind of that thing was absolutely ready since 25, 30 years. It was not implemented just because the people say, who cares about lung volume? So nobody had pushed to have this kind of information. I don't want to go into detail, but if you start with some amount of nitrogen, some amount of oxygen, and some amount of CO2 into the lung, which depends on the air concentration times the tidal volume, the lung volume, if you change the two and you know the new concentration, you can derive the unknown quantity with the lung volume, which is the difference that you have in nitrogen divide the difference that you have between the FiO2 you changed and the previous FiO2. Also, this one is a little bit more complicated in mathematics than before, but not very, very, very complicated. But as the same concept of the helium, you have to reach the equilibrium of gases with a new FiO2 and with a new helium concentration, while the CT doesn't have. Okay? Then we have the indirect methods. This is published in 1988, in which, when we start with the quantitative analysis of the CT scan, we went to what was the dogma at the time, that the RDS lung is stiff. That means the compliance is low. Even now, if you take a textbook, the RDS lung are stiff. So are stiff, more diseases are stiffer they should be. Quite logical. So we expect that correlating the amount of the bad lung measured by the CT scan, the amount of disease, you should find a correlation with the compliance. Absolutely not. After 6 or 7 months, in August, why to look at the glasses half empty? Just look at the glasses half full. And was clearly, it came out that when we measure the compliance, what we measure? We measure the compliance of the open lung, not of the closed lung. So if I have a BB lung of 300 of good lung, at which are associated 1 kilo, 2 kilos, 3 kilos of bad lung, 1, 2, 3 kilos of bad lung are not measured. What I measure with the compliance is the residual good lung. And these are very few patients, but you see very well correlation between the amount of the good lung and the compliance, very roughly. When you have 20 of compliance, we may estimate that the expected lung of that patient, let's say maybe 3 liters, only 20% are still working. So about 600 milliliters, okay? And these very few patients, now 200 patients, you see that the reality is still there, but you start to see which are the standard deviation. Because not all the patients are equal. In this category are patients with different age, anyway, when you start to correct for the different variables, at the end, you come out with one single patient. Because the dream of the statistics, well, we took 2 million here and 2 million there, and we looked at the effect of having 2 grams of sodium per day. New England Journal of Medicine 3 weeks ago. And we found in one paper that everybody was dying. And the other group found that if you don't have at least 4 grams per day, you are dead. And you said, my God, exactly the contrary result. But because this perfect system pretend in thousands of patients to have a perfect equalization, that the statistics take care of the difference of age, taste, hormone level, day and night, whatever. So they all 1,000 things, they make everybody of us an individual man. And we take care of the individual. So in the individual, when you have 20 of compliance, you know that this lung, I'm speaking about acute lung injury, his lung is reduced. How much exactly is reduced? I don't have an idea. I have to measure if I want to take care of this patient and not of the population. But quite clearly, the low compliance is an indication that something is wrong. But most of the patients have a compliance around 40, 50. Now 40 may be decent for the man on my right and may be horrible for the man on my left, because all these numbers have some variability in this sense and this is two sense. And at the end of the story, you have always a cross, which may be a message. Okay. Back Another indirect system, I told you before, if I have strain and transpulmonary pressure, which are linked by a proportionality constant, if my proportionality constant is constant, I measure one, I keep the other one. Okay? Now the problem is that the specific elastance is really constant. What means specific elastance? First, what means is difficult to explain the transpulmonary pressure, because nothing is easier than say, oh my God, you take the alveolar pressure minus the pleural pressure, you get the transpulmonary pressure. What is the problem? But what does really mean? I try to explain how I try to understand this. It takes me decades, I think, to really get the concept. If I take a lung, and you say also, or can you read, that the pressure are transmitted to the pleural space, right? Now, try to take a lung and suspend the lung in the air without chest wall around. And I put into the lung 10, 20, 30, 40, 50 centimeters of pressure. I go to measure the pleural pressure. What I read? 0, 0, 0, 0. I read atmospheric pressure, right? So all the pressure of the airway is spent to move the lung. And how the lung reacts? Developing into its network a force which opposes to the force I apply with the ventilator. This internal force is called stress. So the stress is not the pressure applied, it's the pressure which develops into the lung molecules, which is equal with a different sign than the applied pressure. Is the old dear Newton law, right? So if I apply 30, they react with minus 30, and they get in equilibrium. Okay, this is the transpulmonary pressure, which is equal to stress. Now, my pleural pressure around is 0. Now, let's see, I've wrapped my lung with something very, 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 very soft and very, very elastic. I put my pressure 10, 15, 30, and I go to read the pressure between the lung, which moves, and the elastics, which is around. To move the external body, I have to push. If I push here and measure the pressure, I measure the pressure. This is the intrapleural pressure, which is the motor of the chest wall. So, the airway pressure, the plateau, 36 plateau, are 36 euros that I spend each breath to do what? Maybe 25 to inflate the lung of 1 liter, and 25, 11 to push the lung to the chest wall outside. If the chest is very, very slow, very soft, the pleural pressure will be very low, and if it's very strong, the pleural pressure will be very high. And remember, the heart, the big vessels are subjected to the pleural pressure. So if I have the lung which is very stiff, let's see, I cannot expand the lung. Whatever pressure I put, I increase the pleural pressure without moving anything. But can you imagine what's happened to the heart and the blood vessel? So anytime you have a very high elastance, be careful with the hemodynamic. Anytime you have very high lung elastance, be careful with the lung damage because the stress is very high. So, and now I give you 2-3 numbers that if you will remember that at the end of these 45 minutes, I'll be most happy. Man, transpulmonary pressure, strain. Let's see, I want to know what is my specific elastance. Said it several ways. Tell you the simpler. I measure on my friend 40, come out of anesthesia, measure the FRC is 3 liters. Okay? Now I take a syringe, a big syringe, or I inflate his lung with 3 liters. So I put a tidal volume which is equal to the lung volume. I stop. What is 3 liters divide 3 liters is equal to 1. Now I go to read my specific elastance. I read the specific elastance is equal to the transpulmonary pressure. So the transpulmonary pressure, excuse me, remember this, the specific elastance is the transpulmonary pressure which allows to double the resting lung size. So if I start with 300 milliliters and I put a volume of 300, how much I read? In men, I read something around 12. If I take one man of 5 liters and I put 5 liters, I read 12. Even in patients with ARDS, because the baby lung, his intrinsic characteristics are not so, there are a little bit of fibrosis, little bit of deficit surfactant, but are not so big, apparently, to disturb the intrinsic mechanical characteristics. So let's see, I read the man with 36. If I would know the lung volume, let's see, or if I would know the transpulmonary pressure, the chest wall elastance, let's see that on 36, 6 are for the lung, to move the thorax, and 30 to move the lung. At 12, I know that I double. At 24, it's 3 times. At 30, I'm absolutely at the limit. I'm ventilating at the top of the total lung capacity. Anytime I read 12 of transpulmonary pressure, I know that I'm more or less doubling. They say, you are crazy. How is possible? Look this one. These are patients with RDS and patients without RDS, normal patient. Straight line until you reach the total lung capacity. This is the transpulmonary pressure. This is the strain. If it's a straight line, the slope is transpulmonary pressure divide lung strain, which is equal to the specific elastance. How much is the slope of these things? Is around a strain of 1, I read around 12. Great cartoon. Book of Applied Physiology, 1960. Mead, Agostoni, Weibel, and you see that when you double the FRC, which is here, this is the transpulmonary pressure, what you read? About 12. In COPD, this number is around 20. But there is very little of literature. Just MacLean published 1 paper on it. But you are quite young to have a big sea to explore in terms of the different condition of this kind of patient. And look here. When I double the FRC, strain on 1, my God, I read 6. The specific elastance of the pig is half of the man. You know, when we start the experiments where we are using 40 centimeters of water, and we have about 40% of the PIV went to the CT scan pneumothorax. my God. So we went to measure all this kind of thing, and we discovered that 40 centimeters of water in the pigs is asked to apply about 80, 90 centimeters of water in men. This is why when you speak about stress, strain, and protective strategy in animal, you have to be extremely careful. Try to find out what is the specific elastance of the different species. You can have some indication from 2 or 3 papers, not much. And we continue to play with this kind of game without knowing the basic physiology. This just to tell you that for the same strain, let's see, this is 10 centimeter, no? 10 milliliters per kilo as a substitute strain there. And this is the alveolar dimension. In men is about 10%. In rabbits is 40%, 4 times greater. Because the rabbit, the chest wall of the rabbit start to fly. Is extremely soft. In the man, is different. In the pigs, is between. So anytime you read the literature, be careful. And these are pigs which are ventilated with little ventilation. And we wanted to see, this is the last slide, because I don't have time to speak about another complication, which is the homogeneity of the lung. So basically, we think if the lung is not homogeneous and apply a strain or a given force, I will be a distribution of the forces more in one side than in another side, okay? That means the total energy will be the same, but the distribution of energy will be different. Is as to look at the pill of Italy, and you look how much is in Berlusconi pockets, in my pockets, okay? The distribution of richness is a little bit different. Now, where should be the force concentrated? Where the lesion should appear first? Should appear where you have more unhomogeneity. And you know what is the more dishomogeneous part in a healthy lung? Is the visceral pleura. Without exception, we start at the beginning. After 5 hours, you see this, a little bubble, nothing else change. But in the subpleural space, you start to have a little bubble. Then you have an increase of the bubble because they behave as a women's socks. Where you have an inhomogeneity, becomes more inhomogeneous, greater distribution, until gas exchange. You know how much was all these lesions were perfectly recruitable. These are just due to the strain at the time course of the strain. By the way, all were fully recruitable and inspiration completely open. And the gas exchange was impaired a little bit, not too much, at the end. These are the times. Here, start with a little strain, you start the first lesion at about 7, 8 hours. Then you have 15 and so on. I will speak about this, I think, during the Congress, because I think it's not the stress and the strain. Stress and strain are manifestation of something. What we put that makes the lung vulnerable. We put energy. And energy is delta volume times delta pressure. If I have a fixed pressure, I don't put any energy. No lesions. If I have a tidal, but this is another story. As we have to ventilate this patient, I would like to remind you that if you want to really understand and to be sure that you are not doing a very terrible thing, and the two extremes are lethal ventilation into the lung, when you spend your 36 euros, mostly for the lung, and the lethal becomes when you are in the range of total lung capacity. So we start with a baby lung. If you have, you multiply twice, plus the maldistribution, you are in this area. In the other regions, very, very well neglected, is the hemodynamic distribution, which is more function of the stiffness of the chest wall. I thank you for the attention.